Dark matter. I get asked what it is, and my best answer is, we haven't a clue. We don't know what it is. We look out in the universe, and 85% of all the gravity that's out there has some mysterious unknown source. We add up all the stars, the galaxies, the planets, the comets, the black holes, the dark clouds, everything out there that we can see, touch, smell, or taste. And it doesn't add up to give us the gravity that we see operating in this universe. So really, we should be calling it the dark force, because we don't know if it's made of matter. It could be a profound misnomer, sending people off in thought directions that might not really be the right path. So dark matter is just simply what we call this thing about which we know nothing, responsible for 85% of the gravity of the cosmos. We've known about dark matter since the 1930s. Back then it was called missing mass. That's what it was called. Because, yeah, there's got to be some mass. Where is it? We can't find it. It's got to be here somewhere, because we got the gravity. If you have the gravity, you got to have the mass. Mass and gravity go together. It's really dark gravity. Actually, we shouldn't call it anything. We should call it Fred. Something that has no meaning, because we don't know what it is to call it. But it is the longest standing unsolved problem in modern astrophysics. You know, as if one profound mystery of the universe is not enough. Recently, dark matter was joined by dark energy as one of the most profound sources of ignorance the astrophysicist faces today. In the late 1990s, teams of researchers led by Saul Perlmutter, Brian Schmidt, and Adam Rees discovered that the expanding universe, itself discovered by Edwin Hubble in the 1920s, was accelerating. That turned out to be a Nobel Prize winning measurement. This force that's making it accelerate, we call it dark energy. But since we don't actually know what it is, we could just as easily call it Barney. All right, that's what I want. Dark matter I'll call Fred, dark energy Barney. It doesn't matter, because they're just placeholder words to accommodate our ignorance. You don't want to read too much into those words. So, here's how it works. If the collective gravity of all the galaxies in the universe were all there was, then the expansion of the universe should be slowing down, not speeding up. Because gravity is an attractive force, resisting the expansion. What we found is that there's a mysterious pressure operating in the vacuum of space, and it's combating the gravity and winning. We don't know its origin. We don't know what it is. We're not even sure of its long-term effects. Turns out, Albert Einstein, after he published his new theory of gravity in 1916, that's, of course, the general theory of relativity, he noticed that it predicted a universe that should either be contracting or expanding. Now, that's odd. How could everything you know, how could the universe do anything if it is everything? This was a profound scientific and philosophical dilemma. Unthinkable concept. And if it's expanding or contracting, compared with what? And so Einstein added a mathematically legitimate term to his equations. That term allowed him to stabilize the collapsing influence of gravity in a way to hold up the universe against its wishes. And that way he could keep the universe the same size, whatever size that was. Within just a few years, however, after Edwin Hubble showed that the universe was indeed expanding, Einstein rapidly withdrew the stabilizing term from his equation. You know what he called it? He called the introduction of that term the greatest blunder of my life. He knew, or he felt deep inside, that that term could not be anything physical. There's nothing in the universe that repels matter. Not on large scale. A magnet can do it, but on large scales, there's no known thing that could repel matter. So this term that he added to his equation, he was very uncomfortable about that. That's what left him to call it the greatest blunder of my life. Turns out, the measurement and existence of dark energy is precisely that term in his equations. What that term in his equations do is exactly what we see dark energy doing in the cosmos? So, in fact, Einstein's greatest blunder was saying that the inclusion of that anti-gravity term was his greatest blunder. Isn't it great to be so smart that you're right even when you're wrong? So, here's what you do. You take the energy contained in what we call dark energy, and it's 70% of all that drives the universe. Include with that percentage the dark matter, and we are driven to the humble, mind-blowing conclusion that 96% of all that is the universe is not anything we even remotely understand. 96%. And that all of our laws of physics, everything we know, love, interact with, and understand, or even can predict anything about the future, that falls into the 4% that remains. Now, actually, it gets worse. Our most successful theory of the universe, quantum physics, allows you to calculate what you might expect to be the energy contained in the vacuum of space. We can do that calculation. It allows it. It predicts that there should be energy there. All right? We do the calculation. Quantum physics, it's never been wrong. It's our best understanding going. When you do that calculation, the answer you get does not match reality. The answer you get is off by a factor of 10 to the 20th power. That's a 1 followed by 120 zeros. Now, that's just embarrassing. I'm sorry. All right? We put forth our best theory to our biggest problem, and it gets us nowhere. In fact, it is the biggest mismatch between theory and observation that there ever was in the history of science. That's our state. That's our state of the science today. So, we are not only ignorant, our best theories in the universe can't guide us. So, I think that means we're driving blind.